Welcome everybody to another session from Nairo and Srijit here. So in this session, I'm going to continue the analysis of our density of state. So the graphical representation is one of the crucial part of the density of analysis. Density of state analysis for conveying the key informations related to what are the different descriptions resulting from the density of state and potentially the partial density of state, which we can brief in this following session. So last session I have covered about the various properties related to band gap and density of state. So today I'm just giving you the further analysis part of this density of state calculations. So briefing the density of state analysis of molybdenum disulfide, which we have taken the example with the graphical interpretation. We perform the density of state analysis for this molybdenum disulfide using AMS band to understand its electronic structure, and resulting the density of state graph plots the number of electronic states per unit energy, uh, either in states or electron volt, onto the y-axis, and against the energy on the x-axis. Typically, with the Fermi level, the energy of the highest occupied electronic state at absolute zero, it's set as 0 eV. And then, what are the key features which we can explain in this graph? The first one is the band gap, the most prominent feature of this graph for semiconducting phases of molybdenum disulfide, like the 2H phase, which is a band gap, a region around the Fermi level where the density of state is 0, and it's very low. So this gap separates the valence band, or otherwise known as the occupied states at lower energies, from the conduction band, or the unoccupied states at higher energies. The width of the gap on this energy axis directly corresponds to the band gap energy. For example, if it is a monolayer, we would observe a clear gap of approximately, for example, or calculated our expected value should be around 1.8 electron volt. So in this context, for metallic phases like 1T molybdenum disulfide, the density of state graph would show a significant number of states present at the Fermi level, indicating no band gap, and thus its metallic nature may become stable. For example, let me point out an typical example in this case. Just selecting one metal. So this is actually the molybdenum which I have selected, and if we go to this partial character, let's check with the D density of state, and then I'm just checking the P density of state. So you can see the differences in representation. So in the previous session, I have already briefed about valence band and conduction band. So by analyzing this partial density, or this PDOS overlaid on the total density of state, we can identify the atomic as well as orbital contributions to the valence band. In the case of molybdenum disulfide, the valence band typically has significant contributions from the sp orbitals and molybdenum's d orbitals. S means the sulfide p orbitals, and the molybdenum d orbitals. And speaking about the conduction band, the periodic density of state in the conduction band region reveals the primary atomic as well as orbital character of the states that the electron will occupy when it is got excited. So again, for this molybdenum disulfide, the d orbitals often play a significant role in the lower part of the conduction band. So I have taken two examples here, p and d states of molybdenum. And the vertical line at 0 electron volt on the energy axis represents the Fermi level. So this is actually the Fermi level in this case, but it is not up to 0, it is a little bit diverted. So in the case of an intrinsic semiconductor like molybdenum disulfide, the Fermi level typically lies within the band gap closer to the valence or conduction band, depending on the doping or intrinsic difference. So the value of the density of state at Fermi level is the key indicator of the material's electrical conductivity. A zero or very low density of state at the Fermi level signifies the semiconducting or insulating behavior, with the high density of state indicates the metallic behavior. So since we are taking transition metals and intertransition metal examples, definitely this metallic character or metallic behavior is very important, and how we can prove with the help of band gap calculations. So the peaks of the density of state graph corresponds to the energies with a higher concentration of electronic states. The height and width of these peaks provide information about the number of available states at the specific energy levels. So by examining the partial density of states, we can attribute these peaks to the dominant atomic orbital contributing to those energies, giving insights into the nature of chemical bonding and electronic transitions. So let me go to the output file so we will get a more theoretical idea about this so-called results, and let me show you what is actually the band gap information from this image. So this is actually the band gap information for this molybdenum disulfide calculations. How many number of valence electrons, the valence band index, the top valence band, bottom of the conduction band, the valence band at K points, etc. And also the indirect band gap informations in various units. And also if we take the Fermi level, so you can see the spin as well as the different inputs related to partial density of state, the lattice, the reciprocal lattice, which we have discussed in our previous video, the cell parameters, which defines the angles in degrees, the Bravais lattices. So we have taken a hexagonal uh, structure, the high symmetry points, and also the band structure informations or the band gap from band structure, the value, the atomic charge analysis, and also at the bottom you can see the timing statistics, where we have defined the calculations with the help of this band engine for the molybdenum disulfide. And you can see that the Fermi has been highlighted here, and how much time it has taken to finish this calculation. So in summary, so this AMS band analysis of molybdenum disulfide yielded the graphical representation of density of state that clearly illustrates its electronic structure. For the 2H phase, the presence of distinct band gap around the Fermi level confirms its semiconducting nature, which we have just analyzed with this statistics. The partial density of state analysis further reveals that valence band is primarily composed of p orbitals of sulfur and d states or orbitals of molybdenum, while the lower conduction band has significant molybdenum d character. The absence of the states at the Fermi level in the semiconducting phase indicates low intrinsic conductivity. The detailed picture of the electronic states and the band gap is crucial for understanding and predicting the molybdenum disulfide electric and I mean that molybdenum disulfide's electrical and optical properties. So by structuring this brief story around the key features will be visible in the density of state and partial density of state graph, which will help effectively in communicating the result of our analysis. So thank you.